my topic was the smart BIM object for intelligence modular construction. It means that I have to mix and use a smart BIM object or also AI and in an environment of modular construction. I try to actually in this dissertation I try to create a script by Python to solve a manual process of panelizing and to make it automatic. So for the introduction, I can say that Chuck Eastman in his handbook for BIM declared that during 50 years ago, most of the technologies and industries increase their productivity, but you can see this graph that in AEC industry it cannot do that, and it does not improve as well as the others, and it has some main causes. For example, the products are unique, unable to move, and they are dependent to geographical location and climate, and also I can see and the complexity of the product. It has a lot of elements and a lot of methods. So for increasing the productivity of AEC industry, we can use some new technologies: building information modeling, offsite construction, and modular construction. And in modular construction, we have we have a lot of technologies, and it's not very new, the mass production, but the mass production is not suitable for the for construction, because almost all the final products, I mean the buildings, are unique. So so the mass production cannot be fit to it. But in recent years, we have CNC machines, robots, and the same technologies that introduce a new method in manufacturing called engineer to order. It means that you can design the element, order it to manufacturer or fabricator, and they can produce that element exactly as your design with CNC machines or robots. So our approach is to engineering to order, to produce the elements with ETO approach. And here I have in BIM technology, we can produce or create smart objects that can I can see that they can adjust themselves in a design automatically. We have I think in my literature review I can realize that we have 5 methods: inbuilt parametric objects, family templates, macro scripts, visual programming like Dynamo and Grasshopper, and using the API of BIM authoring softwares for programming. That after I try some of these ways, and finally I decide to use the API of the softwares and create my process in coding by Python. My proposed framework is about the modular construction. It's a sharing area of modular construction, building information modeling, engineering to order, manufacturing, and also artificial intelligence. Here, I want to explain the problem. It's a very BIM and AI is a very, very expanded area, and I prefer to find a specific problem and solve it practically. So, in my dissertation, I was working with the Fractosh company. It's a kind of fabricator that produce some prefabricated panels for walls, roofs, and floors. The method of producing these panels are ETO. It means that you can give them the size and they can produce the panels for you. So it's not a mass production, and they can your order panels can be varied in dimension, also in their details. The problem that they faced to it was there was two problems. First, to arrange panels in an element, a building element, for example, a floor or a roof, and also to how to automate the detailing of that panels. For example, the connections, the thickness of profile, the thickness of the panel, and so on. I decided to solve this problem, the first problem, how to arrange the panels in a floor or a wall or a roof that in most optimized way. There was two options for me: blind optimization, that I can use the Galapagos in Grasshopper, or refinery in Dynamo. They are the same, and it can find the best way that how it can be a curve of a boundary of a panel of a floor, for example, can be panelized in the most optimized way. But it has some problem that I explain to you. The other way was that I called it rational optimization. For example, in that company, the people, the engineers start to divide a floor to some big rectangles, and after that, panelize each rectangle in an optimized way. But I compare these two methods together, and the most important things was that the blind optimization cannot work with ETO approach. It can work with mass production, because the size of the panels, or all of the panels, are the same. But in the rational optimization, you can vary the size, and also you can put in different directions. It has 5 stages, the rational optimization, 5 stages. The first and the last one are about the input and output that I pass them, but the main stages are 3. Division algorithm, that the algorithm start to divide the boundary to some rectangles. After that, pass it to another algorithm. I called it joining algorithm. It starts to find some small rectangles that cannot be panelized regarding to the rules of the production rules that fabricator introduced. It starts to find that small rectangles and join it with its neighbors. And the last or the fourth stage is to panelizing algorithm, that it starts to evaluate each shape that came from joining algorithm. It starts to evaluate them and how to panelize it in the best way. I prefer here to share another PDF. It's a diagram for panelizing the first, the second, and the fourth. The first thing is that, okay, we have this shape of, for example, a floor, a boundary, 2 voids, and 4 small holes for columns. The first function get that curves and start to realize them. Okay, which one is boundary, which one are void, and which one are ignorable curves that the producer, the fabricator says that, okay, if the shape are smaller than a specific size, you can ignore them. And the fabricator or user can here adjust some parameters for extract branches. After that, I clean the branch. It means that, for example, here a void is aligned in the boundary, and so the algorithm starts to clean it and extract this shape. After that, I start to find the biggest rectangle in this shape. There is a question, is the boundary a big boy? Big boy means biggest rectangle that can possible find in here. I think that my time is finished. Can I extend or not? Can I continue or not?
2 more minutes.
Okay. So I defined some functions to find the rectangles. It starts to find the rectangles, all of the rectangles that can be surrounded in that boundary and does not intersect with the voids. After that, some questions, and if they are surrounded by boundary or not. And here it finds the biggest rectangle. When it finds the biggest rectangle, subtract the rectangle from the boundary and save it in a repository. And again, pass the breadth of the shape, like here, to the first algorithm, okay, to again realize it, clean it, and do this cycle repeatedly. After that, we found this division. It goes to the next algorithm. For example, here we have some rules from the fabricator. Okay, you have some rectangle here, but we cannot panelize this rectangle because they are smaller than specific size. This algorithm starts to find, for example, here to find the neighborhoods, the neighbors of these tad boys. I call these tad boys, and after that, evaluate the junction. For example, it's better to join to this neighbor or to that one or the other one. Here we can the algorithm start to evaluate the junction and decide how to join this tad boy to one of its neighbors. For example, after some evaluation, you can, in the end, you can find, okay, the junction that they evaluate them and save them in a, for example, single big boys, that they are not adopted any tad boys. the junction that it means that a big boy with for example, a tad boy that produce a new shape. And also we have earthen boys. It means that maybe we find a small rectangle that cannot be joined regarding to our rules here, evaluation criteria for junction. And they are also, sometimes we found some earthen boys that cannot be joined to their neighbors. Earthen boys must manually edit. It means that you cannot panelize it. Maybe you cover it with another element, or you change your design. You change the boundary of your floor. And in the end, in the last algorithm, we have, for example, these shapes. This one, and this one. And this is a family, that means a big boy adopt a tad boy. And these are the single big boys. Again, the algorithm starts to panelize it. Also, for panelizing, we have some rules from the fabricator. It starts to panelize it in different ways, in different direction, and count the panels and select the best one. For example, here, select the direction that you have to produce less number of panels. And in the end, it intersect the panels with the shape and give you the shape of the panels. And finally, it will be passed to authoring BIM software like Tekla, like Brevit, and create with this geometry that software create the panels for you. Okay, it was, I tried to explain everything in algorithms, but they are these slides, for example, how the algorithm start, how the algorithm evaluate the junction, that which one is better. It starts to evaluate them and score them, and after that select the best one. Or also it's about the rules for analyzing.
Sorry, you'll need to finish.
Fabricator.
Okay,
I finished.
What's the conclusions?
Okay. And the conclusions, I actually, in conclusions, I extract all these algorithms from the way that a human starts to find and panelize a curve, a boundary in an optimized way. And I extract all things from that manual process. And also, I think I have to develop these algorithms, for example, to make it as a plugin, or also this algorithm only can work with a shape that have perpendicular angles, not non-perpendicular. Maybe after that I have time to develop it. And also user-defined rules. It has some rules that user can adjust it, but I want to develop these rules, and that's all.